Welcome back to our Physics Chapter 7 video. And at the end of the last video, we were looking at this example problem, example 712, in which we're trying to find the center of mass of this group of people, these three people sitting on this inflatable banana boat. And so this can be found mathematically by essentially averaging the centers of mass of these three people with respect to some reference point, and we've chosen the back end of the boat as that reference point. So if we take the mass of this person times their distance from the back of the boat, m times 1, and add it to this person's mass, m times 5 meters, and this person mass times 6 meters, we end up with this in the top of our weighted average formula, 1m plus 5m plus 6m, and then we divide by the total mass, m plus m plus m, or 3m. So we end up with 12.0m divided by 3m, and then the m's cancel out, and we just take 12 divided by 3, and we find that the center of mass, xcm we can call it, the x distance to locate the center of mass, is 4.0 meters. So that would be 1, 2, 3, 4, it'd be right here, which is not too far off from where we had guessed, or at least where I had guessed it might be, which, yeah, actually is almost exactly where I had suspected. So if we were to sort of like replace this inflatable boat with a seesaw or a teeter-totter, and we put the center fulcrum of that teeter-totter right here at this 4 meter point, what we are saying is it would balance out, because this person is farther away from the fulcrum than these two are. So even though they all have equal mass, the center of the mass being located here means that this whole boat would balance on that point. Now, for other more irregularly shaped objects, it's not as easy mathematically to find the center of gravity, but it can be done experimentally. So if we had a flat object, like a piece of paper or cardboard or something, and it had some irregular shape, and we wanted to find the center of mass, if we suspended the object from various points along its perimeter and allowed gravity to pull it down, it would do so in such a way that the center of gravity is in line with that point that it's being suspended from. So if we let it hang once, we know that the center of mass is going to be somewhere along that line. And so then if we rotate it some amount and suspend it from a different point, again, the center of mass is going to be directly below that point where it's suspended. And if we've marked the first line there, and then we mark the second line, where they intersect experimentally gives us the center of gravity. Some interesting things about center of mass or center of gravity, I use those terms interchangeably. For instance, a high jumper contorts his body in such a way that although his body travels over the bar, his center of mass may not, because when you consider his legs and arms, that brings the average location of the center of mass down, and so a high jumper can actually go over a bar without his or her center of mass ever going over the bar, which I think is a fascinating bit of trivia. So again, one of the reasons why we are concerned about the center of mass, like in the previous slide where we had the image of the wrench that was being thrown across the screen, and it was rotating as well as translating. We can say that the total mass of that system, the mass of the wrench, for instance, multiplied by the acceleration of the center of mass. So the center of mass was traveling in a straight line. It was not rotating because it's the central point of that rotational motion. So although points on the extreme ends, like the handle or the head of the wrench, were rotating, the center of mass, although it might be spinning, that exact point remains fixed and travels just in a straight line. So the total mass of a system multiplied by the acceleration of the center of mass equals the net force on that system. So this is basically just Newton's second law of motion, stated a little bit more specifically, for big M being the total mass of a system, and this is the acceleration of the center of mass. So if we're looking at something more complicated than a ball, we do a lot of examples with tennis balls or billiard balls, but if we're looking at something that it has a more complicated shape, that might be rotating as well as translating, we can still apply Newton's second law of motion and say that the net force, or sum of forces, is equal to the total amount of mass multiplied by the acceleration of the center of mass. Here's another, I think, really fascinating application of center of mass and how it affects motion. And this comes from the textbook. Basically, what we have here is a rocket that is in two stages. And if it gives itself a certain amount of acceleration, and then essentially the just becomes a projectile. So it accelerates at an upward angle, and then we were to say, cut the engines. At that point, it's no different than a rock or a tennis ball flying through the air. If it remained completely intact, it would follow this path. Okay. If we wanted to extend the path of how far it would travel, if at the highest point, at the peak of this arc, this first stage of the rocket were to be released, and it were to travel straight down, what would happen is, because the mass of this object has been reduced, okay, its momentum is going to make it go farther, because before we had a momentum mv, and that's going to equal the momentum after it releases it. But because the mass has gone down, the velocity will go up, and it will allow this part of the rocket to travel farther. And if we looked at the center of mass of these two objects, even though they are separated now, not physically connected, we could still average the distance between them and find their center of mass. And the interesting thing here is that center of mass continues to follow that original path. So although the projectile is launched and it follows, the center of mass still follows the predicted path, if we drop the mass partway through in such a way that the path of the part one of the rocket here is perpendicular to the direction that path 2 is traveling, we can increase that path of part 2 of the rocket. I just think that's really cool. Okay, excuse me. That brings us to the end of this chapter. Again, I've included in the PowerPoint that I've posted to Blackboard some homework hints here. One thing I want to point out, problem 36. This is something I'll mention here in the video, because I see a misconception with this on both the homework and test questions. So I believe this equation or this problem is about it's about an object that explodes. So we have some object. It explodes and breaks into two pieces. We have a small piece and a large piece, and they're going to fly off in opposite directions from each other, horizontally opposed. So this one object has a larger mass, and this one has a smaller mass. The thing is that initially when the object was at rest, it had no momentum because it had no velocity. And due to the conservation of momentum, that means when these two things fly off in opposite directions, they're going to have equal and opposite momentum that's going to cancel each other out, because we can't just create momentum out of nowhere. If there was none to begin with here, there is the none here when we sum them together, so they're going to cancel each other out. The thing is if this one has a large mass, it would have to have a small volume. And if this one has a small mass, it would have, I'm sorry, not volume, but velocity. So here we have big mass, little velocity. Over here we have little mass, big velocity. And the momentum of these two objects will cancel each other out. So the misconception I see a lot of people have is that the object that has more mass is going to have more momentum. And that's not true, because these two momentums have to cancel each other out. So if this one has a big mass, it has to have small velocity. And this one has a small mass, therefore it has to have a large velocity. And that kind of makes sense if you think about it. If you were to try to throw two rocks, and so assuming that you're giving each of them the same amount of force, you're going to be able to throw the small rock with a much greater velocity than you can throw the big one, right? So that should intuitively make sense, that when you have this object and it explodes and breaks off into two pieces, the bigger piece is going to be moving more slowly than the small piece. The small piece will fly off with a much higher velocity. So don't confuse those. That's my hint for this problem, or just a reminder, I suppose. And I think that's it. So that does it for Chapter 7. If you've got any questions, you can post them to the discussion board. And I'll see you next week with Chapter 8.